Thank you very much. Good morning, everybody. So we'll start the session off with Julie McEnery, who's here from Goddard, and will give us an invited talk on Roman status updates.
Thank you. So before I start, I'd like to express my thanks to the Science Support Center at IPAC for organizing this meeting. The annual Roman Science Conference is the sort of science highlight of the year for Roman. And while, I think we've got a great suite of talks, I also think that folks who are here in person should take advantage of the opportunity to engage with each other, to engage with the representatives from the core community survey committees, to talk to members of the Science Center. You'll learn and hear the status of the mission, what's going on during the talks. You'll hear about the great science people are thinking about in the talks. But there's also real opportunity for informal discussions, and I encourage you to take that. Okay, so I have the delightful privilege of giving an overview talk on the status of the Nancy Grace Roman Space Telescope. And the reason that this is such a privilege is that things are going really well. So before I go into the specifics of where we stand, just a quick recap of what Roman is, and you'll see photographs and movies that show the actual real flight hardware in a moment. We have a telescope of 2.4 meter aperture. That telescope is hidden behind the outer barrel assembly here at the top. Above the telescope is the deployable aperture cover. Below the telescope is the instrument carrier that hosts two instruments. The wide field instrument that does imaging and spectroscopy in the visible to near IR band. And the coronagraph instrument, which operates in the visible to do exoplanet coronography with active wavefront control. We have a large data volume, which is a direct result of having a large field of view and survey mode of operations. We see a lot of the sky very quickly. We're in Sun-Earth L2. I think the single thing that I want you to get away with is we are still working to an October 2026 launch date. That launch date has not changed in years. We had one adjustment in 2020 to account for slowdowns during COVID and have remained on track since then. Okay, so I'm going to start with, a couple of pictures. The telescope is complete. It's currently in 2/3 of the way through vibration testing. It will start thermal vacuum testing next month, which will be an opportunity to test the system cold and counted for gravity. What you see here are pictures of people working on the struts on the left and the telescope in chamber 2B on the right. And then in the middle is the first image of a point source. It looks pretty crappy, but that's because it's before alignment, it's in the air, and has known gravity sag. In fact, the optical performance of the individual elements of the telescope is excellent and everything we had hoped for and more. The wide field instrument, I'm not going to say much here because you'll hear more details from Josh, but the wide field instrument is complete. The pre-ship review is at the end of July and it ships to Goddard in August. I'll say a little bit more about the coronagraph instrument. It also has completed all of its environmental tests. It met its basic requirement of showing that it could meet its level 1 requirements. But then it did more. It pushed wavefront control beyond requirements. It tested a second mask mode. It verified the spectroscopy and polarimetry modes on the coronagraph and collected additional characterization data. So this was all the information needed to allow the coronagraph team and its community group the information to develop the observation plan. And it is sitting currently in the Goddard clean room. And this is the Goddard clean room. This is a picture taken in May. Things are moving really quickly at Goddard right now. So from one week to the next, what you see in this room changes. Much of what's in here are the spacecraft, the deployable aperture cover, the instrument carrier, and the flight solar array shields, but you'll see more of all of this in a moment. Okay, schedule. So this is a super detailed chart that has lots of lines and words that you can't read, and that's all okay, because the point that I want to make is that our elements are either complete or very close to it. Both instruments are complete. The telescope is going through environmental testing. Spacecraft assembly is expected to be completed next month. So we're about to embark on the phase of the mission where we take those individual payload elements, put them together into an observatory and begin observatory level testing. You'll also see, well, you can't see probably because it's really small, but sprinkled through this schedule chart are sections in green. There is more than 3 months of schedule margin to the October 2026 launch date. So, you know, when I say that we're still on track for the October 2026 launch date, we really are. So we're well in hand to meet our requirement of being no later than May 2027. So instead of showing you parts of the spacecraft and the instruction, I'd like to just play a movie. The sound isn't. Can people hear the sound? How do I go back there? That also isn't working. The sound isn't working. This is not so good without sound. No, it's not gonna. So it's not going to work. Okay, that's okay. I'll just play it. So what you're seeing here is there's a soundtrack to this that is makes it pretty spectacular. So what you're seeing is the instrument carrier undergoing testing in the centrifuge. But I'm actually going to skip this. And what I recommend is that people look at my charts and play this with sound, because it really works best if you when you hear the sound, because it's timed very nicely. What you'll see is the activities that have happened in the period from January to May this year. And what we're doing is producing one of these movies every quarter to illustrate the hardware progress that has been made. I think it's very obvious looking at this that a lot of people are putting in a lot of work to bring everything together. Including wide field instrument testing. So in a moment, you'll see the wide field instrument being pushed into the Titan environmental chamber. I think this really illustrates just how big the primary instrument is. And then we end with some shots of the telescope coming together in Rochester. Okay, so moving on. When people talk, typically open a talk about Roman, we talk about the field of view being 200 times larger than the equivalent field on Hubble. But that really only tells a fraction of the story of Roman's capability. We have efficient observations. We have rapid slew and settle. We don't have Earth occultations. We don't go through the South Atlantic anomaly. So we have a lot more on-sky observation time. The relative increase in survey speed between Hubble and Roman is not a factor of 200. It's more like over a factor of 1,000. And I'll illustrate later in this talk what that means for some of the things that we're going to do with Roman. Our science goals drive an observatory that is exceptionally well understood. We need a well understood and stable point spread function, which drives a rigid optical structure with vibration isolation from the spacecraft. That same set of hardware also allows for rapid slew and settle. We move and we're ready to take settle and take the next observation quickly. Josh will talk a little about our hardware on board for the relative calibration system. So it's not just what you have, it's what you do with it that matters. The Roman observation plan is divided into a set of categories. We have most of the observation time will be in 3 very large surveys that provide broad scientific power. These are the core community surveys. The High Latitude Wide Area Survey enables weak lensing and galaxy redshift cosmology objectives, but of course, much, much more. What you see in the word clouds on the right are the keywords from community input that we've solicited over the last year in the process to define these surveys. The High Latitude Time Domain Survey enables the supernova cosmology program, but of course, many, many other topics in time domain and deep field astrophysics. And then finally, the Galactic Bulge Time Domain Survey enables the exoplanet microlensing science objectives and much more. So in the 3 core community surveys, there is an enormous breadth of science. And what we want to do with Roman is excellent astrophysics, exoplanet demographics, and cosmology. And the purpose of the community process to define the surveys is to find that optimal point. We also have at least 25% of the observing time allocated to general astrophysics surveys. These will be defined either via additional community process or through a traditional proposal. We already have our first general astrophysics survey. A galactic plane survey was selected as a topic by a committee that worked very hard last year to identify topics that would scientifically benefit by being defined prior to the first call for proposals. And then finally, we have 90 days for coronagraph technology demonstration observations. So this is an allocation to the coronagraph instrument. So what is done in that 90 days is likely to extend very significantly beyond the basic requirements. I wanted here to pause a little and discuss Roman performance. So if you've been following the W1 and Roman story over the last several years, you'll have a feel for what Roman performance was predicted to be. And the estimates used to evaluate mission performance were necessarily conservative. And as we build the observatory, we know what we have. So we can remove some of that conservatism. So the performance that we are working with to define the core community surveys, to plan general astrophysics surveys, is significantly better than what had been assumed over the last few years. So if you were excited by Roman several years ago, you should be even more excited now. One of the improvements is in slew and settle times. So we have the main change is the ability to run the reaction wheels at their full capability. And this gives us an improved torque, which gives us an improved acceleration. So the way a slew happens, you have an acceleration period, you coast at a maximum rate, which is fixed by safety considerations, and then you decelerate. So the improvement in torque means that that acceleration and deceleration is now faster. And that means that for short slews, you gain a particularly strong advantage. So the decrease in slew speeds caps out at about 20 seconds for sloughs above 2 degrees. But since most Roman sloughs are short, right, we're in the process of dithering through a survey or scaling over a region of the sky, the improvement in the acceleration has a strong impact on the return of the mission. It would allow the high latitude wide area survey to have an extra 100 degrees of sky for free. It would allow the high latitude wide area, the galactic bulge time domain survey with the same cadence to have 8 fields and almost 9, with a corresponding increase in microlensing planet yield, if that is the choice that that survey definition committee make. It would allow the supernova, the observations for the high latitude time domain survey take 1 day less than previously estimated, which gives you a day in hand to do something else, extra spectroscopy, extra cadence, whatever it is. There's also margin in throughput. We will have an updated performance on point spread function and wavefront error. We don't yet have end-to-end measurements, but we do know that it's going to be better than was assumed so far. And then finally, and you'll hear this from Josh, the pixel operability is significantly higher than the requirement. So all of this combines to make an observatory that is better than what you had been assuming several years ago. And I find that very exciting. So coming back to the specifics of the observations, the coronagraph instrument has a 3-month observing allocation. They will spend the first few weeks verifying the level 1 requirements. That's the so-called TTR5. But the remaining time will be available for expanded technology demonstration. This is where we can really think imaginatively about how to use the coronagraph to best help plans for the Habitable Worlds Observatory. You can reasonably expect science to be sprinkled all through these observations, because one of the best ways of doing a technology demonstration is to look at something scientifically rewarding and try and extract the science. The observing program is developed in a collaborative mode with community input that is managed through the community participation program, which I'll talk about later in this talk, if I have time, because I'm going slower than I expected. The core community surveys. This is likely of interest to many, if not everybody in this room. These are the 3 large surveys. The science return from these is going to be spectacular. Something that I found very rewarding was to read the white papers and science pitches that you, the community, submitted to us on what you would like to see, what your hoped for science return is from these surveys. We have 3 survey committees who have been busy evaluating this extensive community input. There are representatives from each of these committees here that are on track for to produce candidate survey designs by this autumn. We have a new survey. I mentioned earlier we had a process to identify whether there was a science case for defining a general astrophysics survey now, and if so, what should that survey be? The committee recommended that yes, we should proceed, and that the survey type should be a galactic plane survey. This is a figure from one of the white papers. So this is a survey of the inner galaxy. It would take a month of observations. So just for reference, a month of Roman observations would take almost a century with Hubble, which is why Hubble hasn't already done this. This survey would have tens of billions of source catalogs and would become the largest object source catalog known. And that's just with 1 month of Roman observation time. So I think this gives you a sense of the power that Roman has, not just for our core community surveys, but beyond. So for the core community survey definition, we have a tiered committee structure. So if you want to imagine, think how the decadal surveys happen, where you've got a set of committees that perform a study that feed their results and reports to a top-level committee that then adjudicate between the options. The top-level committee, we will be issuing a call for self-nominations very soon. The committees themselves have evaluated all of their inputs. They're currently actively working through survey options. I encourage everyone to make sure to be at the sessions this afternoon. What we do with most Roman observing time really needs the active engagement from as broad a segment of the community as possible. You'll hear about these this afternoon. I mentioned that already. And the Galactic Plane General Astrophysics Survey is going to follow broadly a similar process. It started later, so their candidate survey designs will be available this spring. And the chairs of the committee are Bob Benjamin and Rachel Street, and we are in the process of filling out the rest of the committee right now. Okay, so moving away from observations, so you build an observatory, you use it to look at the sky in whatever pattern that you want, and then you need to do something with the data. So what I'm showing here is the data flow for the wide field instrument. Well, a very simplistic, because it doesn't magically go straight from the observatory into exposure level processing. But anyway, the Science Operations Center at the Institute is responsible for exposure level processing. This is the processing step that takes the raw data, up the ramp data, converts it into calibrated pixel level data. The first implementation of that pipeline is complete. The code is publicly available on a GitHub site. The work isn't done. This pipeline is being actively used and tuned based on wide field TVAC data. We're still exploring algorithms. The code is being optimized to run more efficiently. And the specifics of the calibration constants that are used in that pipeline are actively being discussed in the calibration group. So if you want to participate and help shape what that level of processing, oh my God, what that level of processing does, please join the calibration group. For high-level processing, the Roman Science Support Center here at IPAC runs the spectroscopic pipeline and the galactic bulge microlensing pipeline. Both of these also have an initial implementation. Not everything is plugged together into a single pipeline. We're still working on updating and improving algorithms. But the point is that there is something to work with where you can see the actual results. And this is being developed in close partnership with the science teams. Roman's data volume is large, and what that means is that in practice, it will not be easy, and in most cases, not even feasible for you to download the data and process it locally. So our model for how people are going to access the data is via Science Platform, which is in the cloud next to the data. It will be a Jupyter Hub instance, and it gives us lots of advantages in allowing flexible, scalable architecture. What I show here is the plan for the phased release of the Science Platform to the community. So it starts with intense internal development. It will move to selected testing by members of Roman science teams, and then we'll end with broad community usage opportunities with detailed plans for what will be available at each step. So I look forward to everyone here engaging with this and helping us make sure that the Science Platform does what we need it to do and is ready at launch. I'll skip this because I'm going late. Whitefield working groups, because of our data volume And because of our model that it really is going to be, even in the cloud, it's going to be hard to reprocess data from scratch. We need to make sure that the operational pipelines, the calibration pipelines, the higher level pipelines produce science-ready data for as large a fraction of the community as possible. We really do need you to engage. You can work in the calibration pipeline group to follow the processing in the exposure level pipeline. The software group is where you can learn what we're doing with things for catalogs, background modeling. We have a photometric redshift group that is exploring calibrations, algorithms. We've just kicked off a time domain astrophysics group. We have an external synergies, which is a place to find information on how we're engaging with other observatories. And then the ones in gray are groups that have been suggested or about to be formed. To sign up, please follow the link to this for this QR code. It is worth signing up, even if you're not interested in joining any of the working groups. And that's because joining gives you access to the Confluence, the wiki space that the groups are using. These groups are mission level groups that report to the project through the Science Support Center. The support of the groups, the infrastructure, is provided by the Science Operations Center. So they are being very proactive at maintaining a really nice Confluence space, at making the areas easy to browse, at making sure that there are charters so you understand what each group do. This is a huge leap forward from, and I think much more nicely organized than our previous iteration of working groups. I'm going to skip through. There's great things happening with the coronagraph. The coronagraph also has a collaboration and a structure and a plan for enabling engagement even without signing the collaboration agreement. And I finished with, I was going to write some summary, and then I decided that really the only thing you need to know is that we're on track. Thank you.
So we have some minutes for questions if people would like to either raise their hand and then one of the mics will. We'd also really like to encourage younger folks to ask questions.
And I actually should add that the Science Support Center at IPAC provides the equivalent infrastructure support on the coronagraph science community side. So we are taking full advantage of having two excellent science centers supporting us.
Hi, Judy. So what is the expected timeline for the guest observer programs?
The timeline for
Guest observers program.
Yeah, actually, so you mean the guest investigator program? Yeah, so I actually skipped over this, and this is important. We'll have one more call for proposals pre-launch, and this is for additional wide field instrument science and CPP members. Starting 1 year before launch, we will have our first general investigator call, which is operated by the Science Support Center. And this will be an opportunity to propose for funding to support Roman science investigations, because most investigations are likely to use predefined surveys, and also an opportunity to propose for additional general astrophysics surveys. So that's the first call. There will be a call for proposals every year, and roughly every second one will have an opportunity to propose for observations.
Hi, thank you for your talk at John Debus Space Telescope Science Institute. So selfishly, can you talk a little bit about if there are any plans, if the tech demonstration goes well for CGI, what is the thinking for moving beyond that?
Yes, so what's the current plan that is being discussed with headquarters and headquarters advisory committees is that 6 months after the start of science operations, we will have a review of coronagraph instrument performance, and then should everything check out and a case be made, then we'd continue the coronagraph for an additional 18 months. So another 3 months of observations over the next 18 months. We're still working through the plans, but it's likely that we would aim to have a review of wide field performance and surveys and replan mission operations at that, or use that as a trigger point to replan mission operations, because obviously to create space for coronagraph observations, we'd have to refactor the wide field surveys too. Jeff.
This is just a comment about the coronagraph, actually. There's going to be a workshop here at the end of August that will review performance predictions for the coronagraph based on their thermal vacuum test. So if you're actually interested in what you can really do with the coronagraph, that's the place to learn it.
Hi, Julie. I didn't see anyone sign up to give an overview of the galactic plane survey. Can you talk a bit about the boundary conditions again? You know, the amount of time, for example, could it be cadenced in any way? What are the sort of overarching constraints on this? Yeah,
so there aren't many constraints because this survey doesn't have science requirements that it needs to meet. So the white papers, and as a consequence, the committee are going to be considering an area spectroscopy cadence phase space. You know, so I don't know now where this lands. There will need to be some consideration of overlap between, you know, there is already a time domain survey at the galactic bulge. So some aspects of galactic time domain science is done, but I think that this survey in particular is going to have, the committee is going to have to address very profound trades between you know, a complete wide field survey versus time domain capabilities. And you know, the phase space is open for that. The amount of time allocated is a month, so it's not huge relative to the other surveys that people are talking about at the moment.